Hello, this is Mrs. Ballard, and we're going to be talking about topic 1.1 today, which is introducing calculus can occur at a change and can change occur at an instant. So the whole point of today's lesson is it's an introductory lesson over what kind of all of calculus is about. And if you've heard me harp on it before, I already talked to you about it last year that it's all about the slope. That's really a huge part of calculus. So that's what today is about. Don't let it overwhelm you. There's a lot of kind of weird stuff in there today, or stuff that's like seems like it should be further on. We're going to see it again further on. Today is just meant as an introduction. And that's why I had you watch the monster video. The monster video was basically to say, hey, we got to start moving through this. We're going to conquer it, because if we never turn the pages, we might not know that it really isn't as bad as it seems. So today you're going to watch this one. You're also going to watch the ones from AP Classroom and get a slightly different take on it, but there's no written assignments today. All right, so when we're taking notes, as always, we write our last name and our first name up here at the top. And then you can pause this if you want to. We need to write the essential question: what is the difference between change over time and change at an instant? And I can identify change over time versus change at an instant. So the concept of velocity is fairly intuitive. For example, the first leg of Mrs. Ballard's drive to Walt Disney World, the distance from her driveway to Walt Disney World from the distance in her driveway in Hemet, California, is exactly 700 miles to Las Cruces, New Mexico. So we're going exactly 700 miles. If it takes her 10 hours to make the trip, what's her average velocity? Well, that seems pretty intuitive, right? We would take this 700 and we would divide it by 10, which means that I was going 70 miles per hour. Now, we would assume that we'd have to make, what assumption could you make about Mrs. Ballard's driving if the above assumption is true? Well, we know that there's places where posted speed limits are not 70 miles per hour. We know that, like, leaving the neighborhood or leaving Hemet, there's probably places where aren't 70 miles per hour. So if I was going 70 miles per hour at all times, I had to have been speeding somewhere. So likely I was speeding part of the trip, right? Because some places I had to go slower, some places I had to go faster in order to make that average of 70 miles per hour. So she was likely speeding for part of the trip. All right, example 1. Suppose a ball is dropped from the top story of, and I'm not going to try to pronounce that, in this building in Dubai, okay? Which is 2,717 feet from the ground. Find the velocity after 5 seconds. So, by conducting experiments in the late 1500s from atop the Leaning Tower of Pisa, Galileo discovered the distance traveled by a freely falling object is directly proportional to the square of the time it has been falling. In this case, the distance the ball has fallen, s of t after t seconds, can be given by, so they gave us a function for the ball. Okay. We can compute instantaneous velocity at t equals 5 by computing the average velocity over a very short interval of time. For example, t equals 5 to t equals 5.1. So notice they added there's two different sets of words in here: instantaneous versus average. Instantaneous means right at that moment, at that really blink of time. What is happening right at 5.1 seconds? Okay. Average is more like the car, right? What's happening over the exact amount of time, or over a time interval. Okay. There are times that we're going to see this later on where the instantaneous and the average are the same. We're going to see where they are, where I can use the average to estimate the instantaneous, okay? But instantaneous is at that moment. So meaning what was Mrs. Ballard driving in the car at exactly 2 hours in? What was her speed at that time? And then average is over the entire trip. What was her average speed? So we're going to go ahead and make this calculation. I'm going to show you how to do this in Desmos. Whoops, I didn't lose my stuff. Nope, okay. All right, so the great thing about Desmos is that I can type in t's, whereas I can't do that in my calculator. So I'm going to type in the function exactly the way it looks, 16t squared. And then I'm going to go to the next line, and it actually, in the table that comes in the next part of the problem, it actually asks us to calculate the instantaneous at that moment. So I'm going to do s of 5.1, which happens to be 416.16. And then I'm going to set up a formula. So I'm going to use some parentheses. I'm going to go s of 5.1 minus s of 5. So those are my y values. And then I'm going to divide them by my x values, which would be 5.1 minus 5. Hopefully you're recognizing that as x, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, meaning this, all we're doing here is calculating the slope of the of a tangent line to the function. So we're going to look at, so we know it's 161.6. So we know that our average velocity is 100. Average velocity equals 161 point. It's interesting, I got a different number, 0.6. We're just going to go with it. Not that bad. 0.6. And this would be in feet per second. It says use your calculator, in this case Desmos, to obtain 3 other estimates that are progressively more accurate for the instantaneous velocity at time t equals 5. So let's go ahead and use our calculator. We're going to do, I didn't give you the number. So we're going to do 5.01, 5.001, and 5.0001. So basically what I'm doing is I'm trying to get closer and closer and closer to our actual value, okay, by making these estimates using my Desmos calculator. So I'm just going to add in a 0 in front of all of these guys since I've already got it set up. So it looks like I've got 401.6016. So this would be 401.6016. And then our slope was 160.16. All right, let's go back over here. Now I'm going to put in another 0, another 0, and another 0. And we've got 400.106002, and then 160.016. All right, I don't know, our mine. Yep, okay, and then I'm going to go one more decimal place, so 0, 0, oops, not 9, 0, and a 0. Okay, so we're going to write those ones down, okay? All right, so which is 400.016. I did not give you enough space to do the 0.016. And then this column would have been 160.0016. So you'll notice that my instantaneous looks like it's getting really close to 400, and my average velocity, so this was your instantaneous, this is the average. And then my average looks like it's getting to, actually, no, that wasn't instantaneous. That's your actual value of the function, okay? So it's not instantaneous. It's getting really, really, really close to 160. And what we're actually doing here is the concept of a limit, which is what we're going to study starting tomorrow. All right, we've got one more here that we're going to do. So this is, so first of all, there's some things in here. This is actually part of a free response question. You don't need to know really much other than how to calculate slope of a line to do this part of the question. Okay, so you're actually doing your first part of a free response question right now. Isn't that exciting? So there's some words in here that we don't need to worry about yet. You'll eventually learn them. The term twice differentiable and the functions with the symbols h prime are concepts taught later. For now, think of h prime as asking for instantaneous rate of change, approximation using an appropriate average rate of change. So basically what we are finding is we are calculating the slope of a line, okay? So the height of a tree is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are in the table above. Use the data in the table to estimate h prime. So basically we're finding the instantaneous or average rate of change. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. So the first thing is I notice that 6 isn't in the table. So I'm going to find the values that are surrounding 6. And I'm going to use those to calculate my slope. So, and I'm going to use this funny label that they gave me, this h prime of 6 equals. All right, so my y values are 11 minus 6, and my x values are 7 minus 5. Remember to always, whichever value you start with, you have to start with that x value as well. When I subtract this, I get 5 halves. So basically what this was saying is we were talking about the height of the tree, but this is a rate. So that we would say the rate the tree is growing is 5 halves, and then we want to label it, and we do this divided by this, meters per year at the time it was 6 years old, because that's where we estimated at. All right, the last little bit of this is just to show you that there's things that that calculus makes much more powerful. A lot of these we're going to learn in AB, but there's some of them that we won't discuss until you take a second year of calculus. But just some things like without calculus, we can calculate secant lines, but with calculus, we can calculate tangent lines. We're going to be getting into that very soon. We can get to average rate of change without calculus, but instantaneous with calculus. When we get into second semester, we know how to take a volume of something like this. We do not know how to take a volume of something that has an odd shape, that's not a standard geometric shape. So calculus allows us to do those things. So today there's a little bit of a summary on the notes. Remember, you're supposed to be answering your essential question in the summary. And don't forget, you have to have 2 comments or questions between the essential question and the summary. Go ahead and watch the AP Classroom videos, because they're going to have a slightly different take on what I did. And again, don't freak out. Just watch them. You don't even have to take notes on them. Just watch them and absorb.